Hello dear students, our today's topic is a very important reaction which is called as Kolbe reaction. This reaction is used for conversion of phenol to salicylic acid. This compound is called as phenol, and this is salicylic acid. Phenol is also called as carbolic acid. Salicylic acid in common system is called as orthohydroxy benzoic acid. In IUPAC nomenclature, this is called as 2-hydroxy benzoic acid. Now we will wonder why it is called as salicylic acid. If you look at this structure, you will find presence of two functional groups. The one is hydroxy group and the second one is the carboxyl group. Now as per the priority order of the functional groups, the carboxylic acids have priority over the hydroxyl group. So the carbon which is attached with COOH is called as carbon number 1. So its adjacent position is called as position number 2. So as per this system, we will find that on second carbon there is a hydroxy group, so it is 2-hydroxy, and this basic system where the COOH is attached with benzene is called as benzoic acid. So in this way it will become 2-hydroxy benzoic acid. So whenever we go for IUPAC nomenclature, we have to use the number system. Now this name orthohydroxy benzoic acid is adopted in the common system. In common system, we always have to use the prefixes like ortho, meta and para. The carbon to which COOH group is attached is the basic moiety. The carbon which is adjacent to this position is called as the orthocarbon. So on orthocarbon we have the hydroxy group. So in common system it is called as orthohydroxy benzoic acid. So conversion of phenol to salicylic acid takes place in presence of sodium hydroxide, that is NaOH, in presence of carbon dioxide CO2. Here some reaction conditions are used. For example, an elevated temperature of around 125 degrees centigrade and somewhat high pressure of 4 to 7 atmosphere. In the last step, we will use an acid which will convert the salt into corresponding free carboxylic acid. So for conversion of phenol into salicylic acid, these three things are required. First is NaOH, sodium hydroxide. Second is carbon dioxide at elevated temperature of 125 degrees centigrade and a high pressure of 4 to 7 atmosphere. Now again the question is why these reaction conditions are used. Now first thing is that the carbon dioxide is a weak electrophile. So for its attachment on benzene ring, some special conditions are used. That is use of NaOH, a high temperature of 125 degrees centigrade and a high pressure of 4 to 7 atmosphere. This salicylic acid is an important precursor for a very important medicinal compound which is called as aspirin. So salicylic acid when treated with acetic anhydride undergoes conversion into its acetyl derivative like this. This derivative is called as acetyl salicylic acid and generally it is called as aspirin. Aspirin is very important non-steroidal anti-inflammatory drug which is used in the treatment of some conditions like headache and other body aches. Now our main point is conversion of phenol into salicylic acid. So let's look how this conversion takes place. Our starting material is phenol. So phenol is first converted into its sodium salt by reaction with sodium hydroxide. Sorry, it is sodium phenoxide. Phenol is acidic in nature. That means it has such kind of a structure where there is a negative charge on oxygen and a positive charge on hydrogen. Sodium hydroxide is also ionic and it has a positive charge on sodium and a negative charge on hydroxide ion. So when phenol treated with sodium hydroxide, this H plus ion and this OH minus combine together to form water molecule which is liberated out in this reaction. This sodium then combine with this O negative to form sodium phenoxide. Now the question is why phenol gets converted to sodium phenoxide. If we look at the structure, we will find that there is no negative charge on oxygen of phenol, while in sodium phenoxide there is a full negative charge on oxygen. That means this phenoxide ion have a negative charge on oxygen which can be shared through resonance with this benzene ring. So when this negative charge, that means a pair of electron, is shared with the benzene ring, the electron density on benzene ring is increased. In that case, we arrive at some canonical structures, that is the distribution of negative charge on the benzene ring. Now, if we look at these canonical structures, we find that the structures will be like this. When this oxygen forms a bond with this carbon, a double bond gets generated over here like this. When the double bond between oxygen and this carbon takes place, now this pi bond will be broken down and the electron of this pi bond now will be available on this carbon. To satisfy the valency of this carbon, this double bond will be shifted at this position. So this structure then gets converted into this structure. That means for satisfaction of valency, this bond will be shifted and there will be the bond between this carbon and this carbon. So this electron now will be available at this position. Again, to satisfy the valency of this carbon, this double bond will shift from this position to this position. So here we get one more resonating structure. Like this. That means here will be the bond formation between this carbon and this carbon. So this electron density now will be available at this position. Again, to satisfy the valency of this carbon, this structure will have a resonance with this structure. So due to transfer of electrons from oxygen to the carbons of benzene, we have this four resonating structure where the electrons are available at this position, this position, this position, and finally on the oxygen. If we look more closely, we will find that the electrons are more available on the ortho position of this resonating structure. So due to availability of electrons on the ortho position, any electrophile can attack on benzene ring at ortho position. So when sodium phenoxide is treated with carbon dioxide, the carbon dioxide molecule will get attached on to the ortho position because the electrons are more available at the ortho position. Now let's look how this attachment takes place. This is a carbon dioxide molecule. Here is a presence of two pi bond between carbon and oxygen. Oxygens are electronegative elements, so they will attract the electron pair themselves and thus acquire the negative charge. So both the oxygens are partially negative while the carbon is partial positive character. Partial positive means the carbon is in need of electrons now, which are available on ortho position of the phenoxide molecule. So this carbon then attack on the ortho position of phenoxide ion to give us an intermediate. The intermediate formed over here is this one. This is the intermediate species formed during the reaction. When the carbon is developing a bond between this carbon, so the partial bond formation takes place. When this bond formation is partially taking place, the bond between carbon and hydrogen is partially broken down. During this time, the aromaticity of benzene ring is somewhat, or to a lesser extent, is gets disturbed. That's why it is shown by these dotted lines. And though benzene is sharing its electron with carbon dioxide, it will acquire a positive charge. So this species where there is a positive charge on benzene is called as benzenonium ion. As I have told that the aromaticity is partially disturbed. To retain the full aromaticity, this bond between carbon and hydrogen will get broken down. The hydrogen will then migrate over this oxygen. When this bond is broken down, the electron of this bond are then fully available at this carbon, due to which bond between this carbon and this carbon takes place very easily. So in this case, now we will get this product. Now in this product, it will be an acid. So it is the tendency of acid to liberate the proton. So the hydrogen of this carboxyl group will migrate over to the oxygen to make it a free hydroxyl group, while the sodium now will migrate over the oxygen to form the sodium salt. So at this stage, we obtained this sodium salicylate. This species is called as sodium salicylate. This, on treatment with sulfuric acid, gives us the free acid which is called as salicylic acid. The sulfuric acid is a diprotic acid and readily gives the H plus ion. So this H plus ion given by sulfuric acid will migrate over to the carboxylate ion to make it a free COOH. The sodium liberated from here will make an ionic bond with the bisulfate ion. So here it is removal of sodium bisulfate. So this is the simplified mechanism for preparation of salicylic acid from phenol. That is all about the Kolbe reaction. Thanks for watching the video. Please like it, share it, and don't forget to subscribe. Thank you.